What is up, ladies and gentlemen? I am here with a physics tutorial on our second forces and free body diagrams problem set. In this problem, we have a sailboat sitting atop some water. It's got sails up and anchor down stationary. We know the density of water. We know how much water it displaces when it was submerged. We want to find the maximum weight that our boat can carry without sinking. This is actually an incredibly easy problem, which is good. So let's go ahead and see what we've got here. So we've got a boat. There's my boat. It's got the anchor down. Not that this matters necessarily, but anchor is down, and we know that it's stationary as well. Because it's stationary, it's not moving. That means that the net force on it equals 0. The sum of our forces is 0, since it's not moving. So let's go ahead and take a look at what this problem is telling us. We know the density of water is 1,000 kilograms per cubic meter, so density equals 1,000. We know that it's displaced 1,100 cubic meters of water. That's Archimedes' principle. Displacement means volume. And we're looking for maximum weight, of course, being mass. There we go. So, in this problem, we've got this information from the problem. That's cool. Now let's go ahead and take a look at what forces we have acting here. So we know that our net force is 0, so that means that our net force in both directions is going to be 0. We have gravity pulling down, and we have an object on a fluid. So instead of normal force, we get buoyancy or buoyant force. So that's FB. Now, I'm going to call up positive and down negative. Since our net force here is 0, we can say that 0 equals FB minus FG. In other words, FG equals FB. Now, basically, this is the same thing as saying they're equal. If this thing's not moving, it stands to reason that whatever force gravity is pulling down with, the buoyant force is equivalent upwards. And this is really the same principle that our tinfoil boat full of sand problem last week dealt with as well. So, force of gravity is equal to the buoyant force. The net force acting on our boat is going to be 0. Let's look at our equation sheet here and see what these forces are. So first things first, we are not on an incline, right? We're on a flat plane, on a flat, roughly even ocean surface here. So we're going to assume we are not on an incline. There's no angle present. So the force of gravity we're going to use, Fg, is m times 9.8. So we'll go ahead and replace Fg down here with m times 9.8. Force of buoyancy, buoyant force, is going to be 9.8 times rho times v. So that's 9.8 times rho times v. Okay, so now we look over at our variables we wrote down. We have rho, we have v, we're looking for m. We can go ahead and say 9.8 times m equals 9.8 times our density. Density of water being 1,000. And the volume that our boat displaced, which is 1,100 cubic meters. Now is the easy part. Let's see, 9.8 times 1,100 times 1,000. Let me double check and make sure I did that right. 9.8 times 1,100 times 1,000, there we go. $10,780,000. And that's equal to 9.8 times m. Divide both sides of this by 9.8. And, of course, we get mass equals 1,100,000 kilograms. Now, for a large enough boat... Oh, man, my camera. So sorry about that, guys. There we go. So I'll run through this again right quick. Force of gravity is equal to buoyant force. The thing's not moving, so we know they've got to be equal. Using our equations, 9.8 times m for gravity and 9.8 times density times volume for buoyant force. Plug in the 1,000 and the 1,100 from the problem. That gives us 10,780,000 equals 9.8 m. And actually, mathematically too, 9.8 divided by 9.8 is 1. If you wanted to, you could have canceled these back up here and you would have gotten the same thing. And you end up with 1,100,000 kilograms. That's a huge mass. It's about 2 million pounds. It's pretty accurate for the mass of like a first-rate battleship of the line or like an aircraft carrier or something. An enormous vessel might be this heavy, but that's a really easy one. That's how you do it. Hopefully this was helpful. I'll see you guys in the next one.